First, I'm glad you're back. Sorry, these are kind of long, so I decided to split these up into multiple videos so that you can watch them at different times and break them up. Our second example, we're going to use calculus to sketch the curve of the following function. This function is a little bit easier to follow, but we're going to do essentially the same things. First thing we're going to do is we are going to find our y-intercept. And that's always easy because all you got to do is plug in 0, and I plug in 0, this factor becomes 0. This one becomes square root of 9, or 3. 0 times 3 is still 0. So 0, 0 is a y-intercept. That means that it, again, is an x-intercept. So I had 0, 0. But, additionally, when I plug in 9, 9 minus 9 is 0. So this thing becomes 0 when that factor becomes 9. 9 times 0 is also going to give us 0. So 9, 0 is also an x-intercept. There is no symmetry in this graph. The domain of this function is all real numbers that are less than 9. Anything bigger than 9 will make a square root of a negative number, and that is undefined. The range we'll talk about later. And since this is a radical function, it is continuous on its domain. So everything that is less than or equal to 9 will be continuous. And then to find increasing and decreasing, we're going to need to take the first derivative. So let's take that g prime of x. Now, before I start this derivative, I'm going to rewrite this one time and make it x times 9 minus x to the 1/2, so I can use the general power rule on this. It'll need a chain, but it's a fairly simple one. It'll also need a product because it's x times the quantity 9 minus x to the 1/2. So doing the product rule, I leave the first function alone, and then I take the derivative of the second function, so I need to bring the half down. I leave what's inside alone, 9 minus x to the negative 1/2 now when I subtract 1, and then the derivative of 9 minus x is going to be negative 1, and then to that I add the derivative of the first is just going to be 1, and then I leave the second one alone, so negative, or 9 minus x to the 1/2. Okay. So let's simplify a little bit. This thing is going to become x over 2 times 9 minus x to the positive 1/2 on the bottom. And I'm going to need the negative 1, so I'm going to put a negative out in front of the x to take care of that negative 1. And to that I need to add 9 minus x to the 1/2. Alright, so I want to make this into a single fraction, so I need to find a common denominator. So I need to multiply this second term by a funky 1, and it's just going to be 2 times 9 minus x to the 1/2 over 2 times 9 minus x to the 1/2. This function stays the same, it doesn't change, negative x, but I'm going to put it all over the new common denominator, 2 times 9 minus x to the 1/2. And then on the top, it'll be plus. I have that 2, so I'll leave it there. But when I go 9 minus x to the 1/2 times 9 minus x to the 1/2, I add those exponents, and 1/2 plus 1/2 is 1, so I get just 9 minus x. So my final simplification of this thing, when I distribute the 2, I'll have 18 minus 2x plus the negative x. That'll give me 18 minus 3x all over 2 times 9 minus x to the 1/2, and that is going to be my first derivative. Now my critical numbers for this first derivative. There are two critical numbers. Critical numbers exist wherever the first derivative is 0 or undefined. We have one of each in this particular case. In this particular case, we have a critical number at 6 because 18 minus 3 times 6 is 0. So x equal to 6, and then we have an undefined at x equal to 9. Now 9 is on the end point of this particular graph, and we know that because we know the domain, and we talked about the domain. So even though this is a critical number, it's an endpoint. It could potentially be a global minimum or global maximum, although it turns out that it's not. So when I draw in our number line here, I will put both 6 and I'll put 9 here, but 9 is an endpoint, so I won't be testing an interval on the right hand side of that 9. So I want to test this interval from negative infinity to 6. So I want to plug in, let's plug in 0 here. So when I plug in 0, I get positive 18 on the top. When I plug in 0, I get 9 to the half power, which is 3, times 2 is 6, 18 over 6. That's going to be positive. So on that first interval, it's going to be increasing. Now, let's say I pick 7. Now, 7 times 3 is 21. 18 minus 21 is going to give me a negative on the top. All right. When I plug in 7 here, it'll be 2. It'll be the square root of 2 times 2, which will still be positive. So negative on the top, positive on the bottom is going to give me a negative. Okay, so we know since the first derivative is positive from negative infinity to 6, and then negative from 6 to 9, it's increasing until we get to 6 and then decreasing to 9. That tells us that we have a maximum at 6, and then we got to figure out what that value is at 6. So I'm going to go up back to this original and I'll plug in 6. So I got 6, and then 9 minus 6 is going to be 3. So I've got 6 square root of 3, and I'm just going to leave it like that just because that makes it nice and easy for us to write. Now I want to talk about concavity and our points of inflection. So I have to take this second derivative. So f double prime of x is going to equal, okay, I'm going to take the bottom and I'm going to leave that one alone. So 2 times 9 minus x to the 1/2. We're going to leave that alone. We're going to multiply by the derivative of the numerator, which is just going to be negative 3. And then we're going to subtract. We're going to leave the original function alone. So 18 minus 3x. And then we're going to multiply that by the derivative of the bottom. So the derivative of the bottom is going to be 2 times 1/2. Leave the inside alone, so 9 minus x. Subtract 1 from 1/2. That'll give me negative 1/2 times the derivative of what's inside. That's negative 1. And then that will be all over this thing squared. So it's 2 times 9 minus x to the 1/2 quantity squared. All right, so let's try and do a little simplification here. Negative 2 times 3 is negative 6, and then I have my 9 minus x to the 1/2. I'm going to leave this minus out here for a second. I'm going to leave this 18 minus 3x there for a moment. And let's see here. So I get the 2 and the 1/2 cancel. And then if I make this negative 1 and I bring it out here, I can change this to a positive and say that this is just now 9 minus x to the negative 1/2. And then let's see here. We'll square what's on the bottom. So 2 squared is 4. And then 9 minus x to the 1/2 squared will just be 9 minus x. All right, so I've got this negative 1/2. And so what I want to do with that is I am going to put that on the bottom. So I'll have plus, it'll be 18 minus 3x over 9 minus x to the 1/2. And that'll be all over 4 times 9 minus x. So, and this should be 1/2. A little bit better job. Alright, so I want to combine these fractions, so I have to multiply this first fraction by 9 minus x to the 1/2 over 9 minus x to the 1/2, and the 1/2s will cancel, so I'll have 6. Now when I multiply 9 minus x to the 1/2 times 9 minus x to the 1/2, I'll get just 9 minus x. Now it's all going to be over this 9 minus x to the 1/2. But I'm going to add to this the numerator of the second fraction, 18 minus 3x, and that's going to all be over 4 times 9 minus x. Alright, so I'm going to distribute, and then dividing a fraction by a fraction, I'm going to take this and take the reciprocal of it and multiply here. So I'll have negative 6 times 9 is negative 54, and then I'll have positive 6x. And then we'll have plus 18 minus 3x. That will be over 9 minus x to the 1/2, and then we'll multiply that by 1 over 4 times 9 minus x. Oh, this is a biggie. All right, so last simplification. Negative 54 and positive 18 is negative 36, and then 6x and negative 3x will be 3x. And then when I multiply 9 minus x to the 1/2 times 4 times 9 minus x, I'll have the 4. But when I multiply these two things that are in the parentheses, I add my exponents, so I'll have 9 minus x to the 3/2. Okay, now again, this is the second derivative, so it doesn't technically have critical numbers, but the zeros of f double prime are x equals, well, what times 3 is 36? Well, 12 is. And I have an undefined at x equal to 9. Now again, 9 is an endpoint. And 12 is outside of the domain. F will never change concavity. All right, it's never going to change concavity simply because there's no place in the actual domain where it's going to change from concave up or concave down. So if I just pick any number in the domain, let's say 0, if I plug in 0 here, I get negative 36. If I plug in 0 here, I'm going to get a positive. Negative divided by a positive is negative. F is always concave down. So I think we can go back up and we have enough to graph this thing. I know we have a 0 at 0, 0. We have a 0 at 9. And then we have a maximum. Where did we say the maximum was? At 6, 3 square root of 6. So 6 square root of 3. I think I said that wrong the first time. It should be 6 square root of 3. And it's always concave down. So I'm going to get a graph that looks like this. It's increasing to 6 and decreasing from 6 to 9. Says our number line here. So put my scale in there for y. I guess I'm pretty happy with that diagram. Okay, last example. Write the equation of a function that with characteristics. So I got to come up with a function that has a vertical asymptote at -5 and no horizontal asymptote. Need to draw a picture. And so at -5, I've got a vertical asymptote. So let's plug in -5 there. Right there. And so I don't want to have a horizontal asymptote. So no horizontal asymptote, that means my numerator, the degree of the numerator has to be bigger than the degree of the denominator. I'm going to go f of x. I need to have x plus 5 in the denominator. That's going to give me my division by 0. And then I need a degree that's bigger than 1 in the top. So just to keep it easy, I'm going to go x squared. And I think that's going to give me what I want. So let's go to Desmos, and we will type that in. So we'll go f of x, and we'll set that equal to x squared over x plus 5. And if we zoom out, we can see, if I draw in x equals -5, like that. There I have my vertical asymptote at -5 and no horizontal asymptote. That's good enough. There are plenty of other right answers. But that's all I got for today, folks. So, the Star Wars Fun fact of the day, the original Death Star is 140 kilometers in diameter. If it were built like most U.S. naval ships today, it would take at least 1.08 times 10 to the 15th tons of steel to make. That's a lot, especially since the entire Earth output of steel is 1.3 billion tons per year. That means it would take 833,000 years just to produce the steel for the superstructure. That's a lot of time. It's crazy. Well, folks, have a great day. That's all I got. Bye.